In this lecture, we study two of the most powerful tools in software engineering, the abstraction function and the rep invariant. These concepts let us reason precisely about whether our implementations are correct and why they stay correct. By the end of this session, you should be able to write precise abstraction functions and rep invariants as comments in your code. You should also understand representation exposure, know how to prevent it, and be able to construct a rep exposure safety argument. And you should understand benevolent side effects, rep changes that do not change the abstract value. An invariant is a property that is always true for every possible runtime state of a program, given it was true at the start. Consider an immutable string. It represents the same value for its entire lifetime. That is an invariant. Or type safety, a variable declared as number always holds a number. Or a loop, where the index stays within bounds on every iteration. Invariants are everywhere. The question is, who is responsible for maintaining them? A well-designed abstract data type preserves its own invariants regardless of what client code does. This is achieved by hiding fields with private and providing access only through carefully specified methods. In this bank account example, balance is private. Clients can only deposit and query. They can never directly set balance to a negative value. The ADT is the sole guardian of its own correctness. Why bother with all this? Because invariants make reasoning far easier. If balance is always non-negative, you never need to wonder whether some other method silently set it to -500. When a bug occurs, it must be inside the ADT itself, not scattered across the entire codebase. Invariants dramatically narrow the search space. The most dangerous threat to an invariant is representation exposure. Representation exposure occurs when code outside the class can directly read or modify the internal representation. This threatens invariants because external code can put the object into an invalid state. It also threatens representation independence. You can no longer change the internal structure without breaking clients. Rep exposure is one of the most common sources of subtle, hard-to-find bugs in object-oriented code. Here is a classic example of rep exposure through public fields. The post class has public author, text, and timestamp fields. Any code anywhere can write post.author equals hacker. Worse, timestamp is a date object, which is mutable. A client can call setHours on it, mutating what should be immutable data. The fix is to make all fields private and writable, and expose them only through getter methods. Both readable and const prevent reassignment, but neither prevents mutation of a mutable object. This is a common point of confusion. You can declare dates as a const array and still call push on it. Push mutates the array, not the variable binding. Similarly, a private readable timestamp field cannot be reassigned, but timestamp.setHours is still perfectly legal. When the type itself is mutable, readable is not enough. Defensive copying is required. Even with private readable rep exposure can still occur through aliasing. If getTimestamp simply returns this.timestamp, it hands out a live reference to the internal date object. A client stores that reference, calls setHours on it, and directly mutates what was supposed to be private internal state. The client holds an alias, a second name for the same object, and uses it to reach inside the abstraction barrier. Defensive copying breaks the aliasing attack by copying mutable objects at the abstraction boundary. Copy in the constructor, do not store the parameter directly. Create a new date from the input's value. Copy out. In every observer that returns a mutable object, return a copy, not the original. The client's date and the internal date are now completely separate objects. Mutations to one cannot affect the other. Here is the complete defensive copying pattern applied to post. The constructor copies the incoming date using new date of timestamp.getTime. The getTimestamp observer returns a fresh copy each time it is called. The internal timestamp field is now fully protected. No alias can reach it. Defensive copying costs time and memory, but the cost of not copying is far higher. Without copies, you get subtle invariant violations that appear at random, mutations at a distance that are nearly impossible to trace, and broken immutability guarantees. The best strategy of all, prefer immutable types like string, number, and bigint. Immutable values need no defensive copying because clients cannot mutate them regardless. To reason precisely, we model two distinct value spaces. The abstract value space, labeled A, contains the values the client sees, for example, a mathematical set containing A, B, and C. The representation space, labeled R, contains the concrete objects the implementer actually uses, for example, a string ABC. The implementer creates the illusion of the abstract space using real objects in R. The client never needs to know how. This diagram shows the two spaces side by side. On the left is the rep space R, the actual data stored in memory. On the right is the abstract space A, the values the client perceives. Arrows represent the abstraction function, mapping valid rep values to their abstract counterparts. Notice the red zone on the left. Some rep values are invalid. They have no arrow. The AF is only defined for rep values that satisfy the rep invariant. This visual captures the entire correctness story for an ADT. The abstraction function, written AF, maps from the rep space R to the abstract space A. It defines exactly how the implementer interprets internal data as an abstract value. For charset with a string rep, AF of rep equals the set of characters at each position. So the string ABC maps to the set containing A, B, and C, and BA maps to the same set as AB because sets are unordered. The AF must be documented as a comment next to the private fields, not in the public type doc. The rep invariant, written RI, is a predicate on rep values. It answers, is this rep well formed? RI of R is true if and only if the AF is defined for R. For charset, the RI says, rep contains no repeated characters. The string ABC satisfies the RI, valid. The string ABC violates it, appears twice. There is no meaningful way to interpret a rep with duplicates as a set. The RI defines the green zone of valid rep values. Here is the first of two possible representations for charset. The no repeats rep stores a string with no duplicate characters. The AF maps that string to the set of its characters. The RI enforces uniqueness. To check membership, you scan through the string linearly, O of n. Simple and correct, but not the fastest option when the character set is large. Here is an alternative representation, sorted. The sorted rep stores a string whose characters are in sorted order. The AF still maps it to the same abstract set. But now the RI enforces sorting rather than just uniqueness. With the characters sorted, binary search becomes possible. Membership checks drop from O of n to O of log n. Notice, same abstract type, same rep type, but a different RI and AF, and completely different performance characteristics. This is the power of representation independence. Clients see only the interface, and you can swap implementations freely. Where do you write the AF and RI? As comments immediately next to the private fields. Not in TypeDoc, which is visible to clients. The AF and RI describe internal implementation details that clients must never see. For ratnum, the RI says, denominator is greater than 0 and the fraction is always fully reduced, that the GCD of numerator and denominator is 1. The AF says, AF of numerator and denominator equals numerator divided by denominator. Be precise. Vague documentation gives false confidence. This diagram maps ratnum rep values, pairs of big int numerator and denominator, to rational number abstract values. In the green zone, fractions with positive denominators in fully reduced form. These have AF arrows pointing to their rational values. In the red zone, fractions with denominator 0, or unreduced fractions like 2 over 4. No AF arrow exists for them. The ratnum constructor must ensure every object it creates lands in the green zone, never in the red. Here is the ratnum constructor. It computes the greatest common divisor of the absolute values of numerator and denominator. It then adjusts the sign. If the denominator was negative, it flips both signs and divides both by the GZD. The result is always a fraction in fully reduced form with a positive denominator. The last line calls checkrep, which verifies the RI holds before the constructor returns. Checkrep implements the rep invariant as a runtime assertion. It throws if the denominator is not positive or if the fraction is not in reduced form. When should you call checkrep? At the end of every creator and producer, at the end of every mutator, Optionally at the start or end of observers, this helps catch rep exposure bugs earlier. Check-rep turns silent invariant violations into loud, immediate failures at the point where the damage occurred. With strict null checking enabled, which is the default in our projects, all rep references are implicitly non-null. You do not need to state field is not null or undefined in your RI. The TypeScript compiler guarantees it. If null or undefined is intentionally valid for a field, you must declare the type explicitly as string or undefined. Strict null checking eliminates an entire class of null pointer bugs at compile time for free. An ADT is immutable if the abstract value never changes. But the representation may change, as long as the AF maps the new rep to the same abstract value. This is a benevolent side effect, a rep mutation that clients cannot observe. Examples include caching a computed result, lazy normalization, or rebalancing an internal data structure. The abstract value is unchanged. The client cannot tell the difference. Here is a concrete benevolent side effect in Ratnum's toString method. The method normalizes the fraction on the first call, reducing 2/4 to 1/2. The abstract value, 0.5, has not changed, but the internal rep has. Since the client only sees the abstract value, this mutation is completely safe. Note, this pattern uses a typecast to bypass TypeScript's retable check. Use it only when you are certain the abstract value is preserved. Documentation must be precise, not vague. A rep invariant that says all fields are valid tells you nothing. One that says denominator greater than 0 and GDD equals 1 is checkable and actionable. An abstraction function that says represents a set of characters tells you nothing. One that says the set equals the characters at each index is precise. Vague documentation looks like documentation. It gives false confidence while leaving the implementation unverified. Every ADT should include a comment explaining why the rep is safe from exposure. The argument must address every field individually. For author and text, they are private readable strings. Strings are immutable in TypeScript, no defensive copy needed. For timestamp, it is a private readable date, which is mutable. Defensive copying is used both in the constructor on the way in and in getTimestamp on the way out. Writing this argument forces you to think carefully about every boundary. A powerful benefit of ADT's well-designed types replace fragile preconditions. Without an ADT, a function operating on sorted character sets must include a precondition in its spec. The caller must ensure the input is sorted with no repeats. This is easy to forget and hard to enforce. With an ADT, the parameter type is sorted charset. Clients cannot create an invalid sorted charset. The constructor enforces the invariant. The type system itself enforces the precondition. The bug simply cannot happen. To prove that an invariant holds for all instances, we use a structural induction argument. Step 1. Every creator and producer must establish the invariant when creating a new instance. Step 2. Every mutator and producer must preserve the invariant, never move an object into the red zone. Step 3. There must be no rep exposure. No external code can bypass the methods and corrupt the rep directly. If all three conditions hold, the invariant is guaranteed for the entire lifetime of every object. Here is the recipe for writing an ADT in order. First, write the spec, operation signatures, pre and post conditions, and the abstract value space. Second, write tests systematically before implementing. Third, implement. Choose the rep and write private fields. Write the AF and RI as comments. Write the rep exposure safety argument. Implement checkrep. Implement the operations calling checkrep where appropriate. Following this order prevents a common mistake, implementing first and only discovering the AF and RI are wrong when something breaks. Let us summarize the key ideas. An invariant is a property always true for all instances. Rep exposure occurs when external code can modify the internal rep. The abstraction function maps rep values to abstract values. The rep invariant is a predicate defining which rep values are valid. Defensive copying protects mutable objects at constructor and observer boundaries. Checkrep asserts the RI at runtime. And a benevolent side effect is a rep change that leaves the abstract value unchanged. Together, these tools let you reason rigorously about correctness.